Okay, sorry for getting started a little late. I think we're officially a minute late, sorry. But thank you so much to everyone for coming to our final lecture of the semester. This one's a little different in that instead of having a professor up here, we are actually going to have various cast students talking about the research they do as undergraduates here at Cornell. So this is a great opportunity to hear about some, not even most or all, but some of the research done by undergraduates around Cornell in various different departments. We are going to have Abby talking about research she does with Lisa Koltenegger. We are going to have Ben talking about research he does with Jim Cordes. Marquise is going to be talking about research he does with Anna Ho. Eric and Claire are going to be talking about research they do with Professor Savransky and Professor Peck. So I will hand it off to Abby whenever she is ready. You guys can clap. There you go.
Thank you.
Gotta get my notes up here. Switch this a little bit. Computer over. Awesome. This is so cool.
Okay, yes. How do I do the next slide? Cool. Okay, so hi everyone. So my name's Abby Bull, and I'm going to be giving you kind of a crash course in the Carl Sagan Institute. So the majority of this presentation is actually not going to be about my research. It's going to be about the research done at the Carl Sagan Institute to kind of just give you all an overview of what we do there and the different areas of research. And it's very multidisciplinary, so you guys just see a little bit of how that goes. So yeah. So this is the Carl Sagan Institute mission statement that you can see that I took from their website. So it's founded to find life in the universe, essentially, with a couple of other things as well. So pretty cool. Finding life in the universe. What that also means, so in other words, we're looking for those guys. So how do you find life in the universe? So you may be thinking, hey, we have this amazing telescope called the James Webb Space Telescope that can be used, sort of, to look at exoplanets. So why don't we just look directly with that? So there's a couple problems, but the one that we'll focus on is, as you can see from this very, very realistic and definitely not photoshopped image, is that there are a lot of stars. And, I know, crazy, right? But excitingly, there are also a lot of exoplanets. So kind of the goal essentially is to figure out where to look and where not to look. So this is my little diagram. You can see those are stars. You don't want to look at them. And then maybe also you can find places where you can look. So it kind of becomes a game of, knowing where to look and then also trying to figure out what you are specifically looking for. So how do we do that? So here are a couple of the pillars of research, as they say on the Carl Sagan Institute. So there are more than this. I think there are around like 6, but I just picked these 3 because they seem like a pretty good overview of the different ways to find life in the universe. So we're going to go through those. So the first one is atmospheric spectral signatures. So the text says that you focus on planets and moons orbiting suns bright enough for future atmospheric follow-up, especially many to super-Earths orbiting in the habitable zones around their host stars. So a pretty good overview, but there's also some kind of confusing things maybe that are in this that I want to go through a little bit more. So specifically, atmospheric spectral signatures. So what is that? So when a planet passes in front of the star, or it transits, some of the light that shines through that planet's atmosphere is blocked by atmospheric molecules in the atmosphere of the planet. And so this forms what we know as a spectra, so you can see that here. And so when we can look at those spectra to figure out the different elements that are inside the planet's atmosphere, right? So I kind of said that 4 different times. But so if there's life on a planet, then biosignatures may appear in the spectra of that planet. So for example, if you see oxygen and methane at the same time in an atmosphere, that could be an indicator of life. And again, we see that by looking at these lines that you can get by looking at transits. So pretty cool. This is a little bit of a side. What's a habitable zone? So the habitable zone is the area around a star where liquid water can exist on the planet's surface. So you might be thinking, well, water can exist in liquid form under the surface of some planets or moons, if you think about Europa. But the point of having the habitable zone be liquid water on the surface is that we want to see the spectra, as you saw on the other side. So those biosignatures that we talked about might not appear in the spectra if the water is below the Earth's surface. So if life is below, we just might not be able to see the life, and we want to find the life. So that's why we choose to look at the liquid water on the Earth's surface. So kind of putting that all together, you've got these habitable zone planets, and then you have these spectra that you can find around them. And so if you look at those, then you may be able to find biosignatures, which would then lead to finding life. So pretty cool. At this point, can't image a lot of the small planets directly, but you know, it's the goal. So this is the second area of research that we're going to be talking about, and it's about engaging with life on Earth. So we use Earth biota as a Rosetta Stone for the search for life on other worlds. We include life forms that are called extreme on our own planet, but could be dominant on other worlds, and develop observing strategies and mission concepts for future searches. So if you guys are at Carl Sagan Night, you might have seen the presentation by Dr. Alicia Coelho. And she recently published this paper called Purple is the New Green, Biomagnetics and Spectra on Earth-like Purple Worlds. It's pretty cool. So the point of that is that other planets could be potentially covered by purple bacteria. So like on Earth, we see a lot of green because it's beneficial for green based on the color of our star. I'm going to try again. That was not a very good explanation. So a lot of the life on Earth is green, as we know. You know, the trees, such things. Organisms on Earth perform oxygen-producing photosynthesis, and they use the green pigment chlorophyll A. But on other worlds, especially those that may not have as much oxygen or light, may use purple bacteria instead. So we look at the purple, we look at biosignatures that could help detect extraterrestrial life by studying the light reflected from planetary surfaces, and we have to look at extreme bacteria to do so. So the last one we're going to talk about is planetary environments. So we examine Earth and solar system input of geophysical fluid dynamics and the thermal evolution of solid planets, the tectonic and glacial volcano features that shape their planets, their surfaces, to model and study a wide range of possible planets and moods inside and outside our own solar system. So again, if you guys were at Carl Sagan Night, you might have seen the work of Professor Brittany Schmidt. And so something that she does, which is pretty cool, is that she has this 13-foot long torpedo-like ice fin that she takes and she puts below the ice at Antarctica. And so she uses that to characterize the sub-ice environments using cameras, sonar, chemical, and biological sensors. So all that stuff on this thing, pretty cool. And then she can then use this data to understand how the ice may work on a planet like Europa. So there's a lot of different research in this area. This is just one, but I think that this is a pretty cool example of that type of research. So this is something that I worked on, talking about myself now, with Gillis and Lucas. Gillis, who you probably all know, and then Lucas, who is a CAS alumni from, I think, 2 years now. We love Lucas. And so the point of this one is a little bit like I was talking earlier, eliminating exoplanets that we cannot find life on. Or in other words, trying to find life, figure out where that life may be, by specifically focusing on the habitable zone parts of this. So we start over here. There's 5,000 plus known exoplanets. I forget the exact number off the top of my head, but that's a lot of exoplanets, and that's a lot of different places to look on the sky. We can then narrow those down to planets that are in the habitable zone, as we talked about before. Those habitable zone planets are the ones that may have liquid water on their surface, or that they should. And so they orbit within their planet's habitable zone, so we can narrow down to just those ones. Then we find the rocky habitable zone planets. Those are going to be the ones that are like Earth. It's either 2 Earth radii, or if we don't have the radii data, less than 5 Earth masses. So that gets us an even smaller subset. And then we want to actually find life, right? And so life takes time to develop. And so we specifically look at the planets that are around stars that are old enough where life may have actually developed on those planets. And so that gets us an even smaller subset and shows us where we should be looking. And so just a quick little diagram here. So this is where the earliest possible life, okay. So age is on this axis, and then the amount of flux or like energy that the planet receives from its host star is on this axis. So the earliest possible life is here. Great oxidation event, multicellular event, animals evolve, humans evolve, right? So if we're looking for intelligent life, we should be looking at specifically those stars and the planets that are around them. So these are the planets that specifically fit into all of the categories that we've looked at. And so if you were like, hey, what's a planet that may have life? Maybe one of these ones. So That's what we do. And yeah, thanks for listening.
Okay. Do we want to do questions between? Do you want to take questions now? Yeah. Does anyone have any quick questions?
I forget off the top of my head. Like one, two, three. Like, I think it was order like actually like 30 or something. Or maybe 60 planets. I don't know. Something like that. I should know this off the top of my head, but I didn't put it in my slides. But it was down from like 5,000 around 60 or something. So yeah, so much fewer, and it depends on whether or not you like. There's a couple of things that it depends on because it's just talking about like specifically the research that we did. So there's a couple of different ways to figure out like go through these different steps. So this was kind of like a simplified overview of the way that we do it. So it depends on a little bit also on like the stellar data that you choose to use, and then like whether or not you want to consider only planets that directly pass. So we were talking about the transit method before. So there's a couple of different ways of finding data from exoplanets, and so transit is one of them. There's also like learning about the radial velocity and seeing how that impacts the star's movement and such things like that. So there's a couple of different ways that you can learn about them. So we have a version of this graph that only uses planets at transit in front of them. And so we were thinking that that's probably the best way to get the actual most accurate data on like the radii. But this one has all of them. So in other words, I think it's around 60 of 5,000, but there's a lot of different parameters that you can play with to figure out like slightly different numbers. So, but like, I mean, pretty cool, right? Like if you're just looking at this, it's very like concrete. This is not something, this is the stellar temperature, and then the size of the planet is the size of these a little as well. So like a bigger one here is going to be a bigger planet versus a smaller one. So, I mean, I don't know. Pretty cool. So yeah, I don't know if that answered the question. But oh, yes. So the question was, how do you get involved at the Carl Sagan Institute? Funny story, actually, for me. I was a freshman, and Professor Lisa Kaltenegger was giving one of these lectures, and I went up afterwards, and I was like, hey, so this is pretty cool, and I was wondering how you could get involved. And she was like, you should email me. And then so I emailed her, and then I've been here since, actually. So I'm a junior now. So the answer to your question is you should email Lisa Kaltenegger. And if she does not respond, you should email her again. So, yeah, she gets a lot of emails, so yeah.
We can give one last thanks to Abby, and we will move on to Ben, who is actually not in Ithaca with us. He fled the cold weather and is in California. So he will be giving his talk. You will hear his voice disembodied in the speakers. And message to Ben, you can tell me when you want to switch your slides because you can't control that at the moment.
That sounds good to me. Hey everyone, greetings from Berkeley. Many thanks to Jillian and everybody else setting this up for being willing to work with me on the geographical distance between. I'm here to talk to you all today about radio astronomy, bringing you into a totally different region of the electromagnetic spectrum and a totally different class of the universe's most extreme objects that we can investigate with radio waves. Radio astronomy is an enormous field spanning. Uh, well, you can do radio astronomy practically anywhere you can do any other kind of astronomy, whatever other objects, whatever other questions you'd like to answer. Seldom are you hurt by adding a new band of the spectrum. But what I'd like to talk to you about today are the main areas of radio astronomy that are focused on at Cornell, which we're going to talk about pulsars, we're going to talk about fast radio bursts, and we're going to talk about an application of pulsars that helps us investigate gravitational waves and learn about our own galaxy and other galaxies near us. I'll take the next slide, please, Julian. So radio astronomy is intro astronomy classes tend not to go into this, and we don't really do it at the observatory much, with a couple of exceptions. It's not really, we don't see radio waves. It's all the way down at the very long wavelength, very low frequency end of the spectrum. This has a lot of practical effects for us. The main one has to do with the Rayleigh criterion. I swear the only equation in my slides, you can see it up there on the screen. I can't gesture to it, but you can probably see it. What the Rayleigh criterion says is that if you want to increase your resolution, the resolution of the image you're seeing, um, down to smaller angles, you want each pixel of your image to represent a smaller angle on the sky. When you increase the wavelength of light you're looking at, that's the lambda up top there. If you want to keep your resolution the same, you also have to increase the diameter of your telescope. So longer wavelength light, you need a much bigger telescope to observe it. Radio waves tend to be 4 or 5 orders of magnitude longer than, for example, visible light, ultraviolet light, in the upper end of the spectrum, and it only gets higher from there. So radio telescopes have to be correspondingly bigger. Our radio telescopes, we can't make them 1,000, 10,000, 100,000 times larger than our best optical telescopes. So there's a bit of a trade-off in terms of resolution. We don't get quite as good resolution with radio telescopes as optical telescopes do, and we sort of have to invent creative ways around that problem. Um, a central thing about radio telescopes that is maybe not immediately obvious is that we're not measuring the entire sky at once. We're not measuring what we're looking at as an image all at the same time. We're looking at, so you can imagine the beam from a radio telescope uh, focusing on some portion of sky, and then all of the light from that beam gets recorded by the telescope at the same time as a single intensity value. It's sort of like your telescope is producing an image that's only 1 pixel, and the brightness of the pixel is however much brightness is in your image. And it does this by recording the voltage, and there's some stuff that goes on with that that we don't really need to get into right now. So radio telescopes can be quite simple. All you really need is an antenna, like a dish antenna for cable TV, um, and a way to measure the intensity of the voltage that's recording. But you can also get quite big. The Arecibo telescope there, I'm a big fan of it. We're all a big fan of it. The Arecibo telescope was 1,000 feet across, and for many years it was the largest telescope in the world. It's been superseded in 2015. Now there's a 500-meter, I guess 1,500 feet across telescope in China. Um, but even these have the same sort of single pixel problem. We don't get good resolution. The beam on the sky, we're looking at like an entire galaxy's worth of stars in one beam. If we look at Andromeda, for instance, and all of that light is being recorded as a single pixel. Um, Now there are exceptions to this. There's the interferometry helps us do different things. This is the process of you can build an array of many telescopes spread out over a large region, sort of like the very large array is the example from Carl Sagan's movie Contact, and there are other arrays around the world. And this is how you get to take really high resolution radio images. Um, the most famous of which being things like the photo of a black hole that you've probably seen, or should have put that on the slide. Oh well. Um, so we can take images of really small things really far away, but we have to build really big telescopes to do it. And building arrays is one way to do that because via interferometry we can make our many telescopes act like a single telescope, and that's a very useful technique in radio astronomy. I'll move on to the next slide for one more difference that epitomizes the radio astronomy, other astronomy divide. Uh, on the left, you see an image I took from Adam Langeveld's paper. He's on the third floor of the Space Sciences building. This is an image from the James Webb Space Telescope of a star-forming nebula, NGC 1333. He's got right ascension on one axis, declination on the other axis, so this is pretty obviously a spatial image. If you cropped out a little portion of it, it would make a good iPhone wallpaper. Radio telescopes, apart from the interferometry case, apart from the array case, you're not you're not looking at images that like that. Certainly not that crisp. If you're making images at all, they're really, really low resolution and ill-defined. So what we do instead is we take the just a single pixel intensity values over time, and through some complex, not really super complex math, Fourier transforms, which you get to in different physics and math classes here. Um, you can convert that time series of intensity values into these dynamic spectra that you see on the middle and the right-hand side of this slide. And these dynamic spectra show time on the x-axis and frequency, observing frequency, radio frequency on the y-axis. And they span the megahertz to gigahertz region of the electromagnetic spectrum, about a factor of a million lower than the upper range of the visible spectrum, which is in like, we're talking about terahertz and hundreds of terahertz in that context. So on these dynamic spectra, we see not like, we don't see circular shapes like stars and nebulae. We see signals, radio signals, being maybe swept out in time and frequency, like you see on these two plots. If they get swept, that's a pretty good indication that the signal is astrophysical. This is due to dispersive effects that we don't really have to go into here. But we also see similar signals from local radio sources like microwave ovens and Wi-Fi transmitters, and these show up as not really drifty, sweepy effects, but more sort of vertical or horizontal lines on these plots. And a lot of radio astronomy is finding the interesting signals in here and sort of decoding the information in them to infer properties of the object that produced them. I'll take the next slide, please. So given the differences between radio astronomy and, for example, optical astronomy, why would you want to do radio astronomy? It's true that in general, you don't get the high resolution images of beautiful nebulae that the James Webb Space Telescope gets. Again, telescopic arrays aside. But radio astronomy has a lot of things going for it. One is that even though the telescopes are truly enormous and cost a lot of money to produce, and there aren't really that many of the really huge ones in the world, they can be in operation all of the time. Radio waves are large enough that they pass through the atmosphere mostly unimpeded. They don't get scattered the way optical light does, turning the sky blue. And that means that the stars and other distant objects are not washed out by sunlight. The Green Bank telescope you see on this slide can observe during the day as well as at night. And as long as you don't point directly at the sun, you're pretty much good to go. You can do radio astronomy whenever you like. And this can also be good for student sleep schedules as well. I'll take the next slide, please. And that's not even to speak of the extreme objects in the universe that are only observable, more or less, through radio waves. Pulsars are the archetypal example. A pulsar is a neutron star, which is sort of the remnant of a star more massive than the sun. When it exhausts the fuel that it uses to burn, it collapses, and under the force of its own gravity, what's left behind is a ball made of mostly basically neutrons. There's not a significant number of protons and electrons in the mix. It's all just kind of a neutron soup. This is extraordinarily dense. Atoms are mostly empty space until you collapse them just into neutrons. So the proverbial example is that you can take a teaspoon out of a neutron star and it would weigh as much as a mountain on Earth. Pulsars are a class of neutron star that emits light from its magnetic poles, the north and south pole. You can see on the right-hand side of the screen here. I'm waving my cursor, but I realize it doesn't do anything on your screen. And since the magnetic field axis is displaced from the rotational axis, as the pulsar spins around, these beams of light get wung around kind of like a lighthouse. The beams of light spin around, and whenever they intersect our line of sight, whenever they pass the Earth, we see that flash of light like a little blip on our receivers. So we see that repeated sweep on the dynamic spectrum I showed a couple slides ago, and that's the hallmark of a pulsar. Fast radio bursts are also interesting. These are sort of like pulsars. They appear very similarly on our dynamic spectra, but they don't repeat as regularly as pulsars. And although they have similar energy profiles, they appear to be coming from much farther away, which suggests that whatever is producing them is a much more energetic emitter than a pulsar is. And still not quite sure what's producing these. So that's an open question that our radio group at Cornell is helping to investigate. And black holes. So black holes, the example I already talked about was you can build an interferometric radio telescope using radio telescopes from around the world and use that to take a really high resolution snapshot of a galactic center, looking at the black hole at the galactic center, and those are the famous black hole images. But black holes are also prodigious producers of gravitational waves. These are ripples in space-time that Einstein predicted from the theory of general relativity. Um, really, really big black holes, talking supermassive black holes like those at the centers of galaxies, when they move in space, orbiting around each other, they give off gravitational waves, sort of like ripples on stones being moved through a pond. These gravitational waves, because the black holes are so massive and the orbital periods are so long, the periods of the gravitational waves are correspondingly long. We expect the peaks to each sort of period of the gravitational wave is on the scale of decades of our Earth years. So it takes a really long time to be able to observe these, and we need really long distances, really long detectors to be able to do so. Fortunately, pulsars scattered all throughout the galaxy sort of provide a neat trick way to do that. Uh, Certain pulsars can be timed really accurately with precisions comparable to those of atomic clocks. And if you are looking at many pulsars all across the sky, any individual pulsar, the ticks might arrive a little bit early or a little bit late for a variety of random reasons. But if you're looking at pulsars all across the sky and all of them are early or late by a similar margin, that's an indication that space-time itself is being messed with in your vicinity, which is the signature of a gravitational wave. So these are called pulsar timing arrays when you set up networks of pulsars to do this, and this is what the NanoGrav collaboration works on here at Cornell. I should say the group at Cornell is part of the larger NanoGrav collaboration. Jillian, could you do the next slide, please? And one final thing about radio waves is that the space between stars, and indeed the space between galaxies, is not completely empty. There's a tenuous gas of electrons that we call the interstellar medium or intergalactic medium, respectively, and it's very, very hard to detect. Optical light passes through it with, basically no problem, but radio waves get dispersed by these electrons due to, again, dispersive forces we're going to gloss over here. But the sweeps that we saw on the waterfall plots, the dynamic spectra, all of that through pulsars and fast radio bursts helps us to learn things like the shape of our galaxy and the shape of the halo around our galaxy and the shapes of the halos of surrounding galaxies. And this ties into dark matter and cosmology and all sorts of other things. My last slide on the next slide is an overview of the radio group here at Cornell. These are our new first year members notwithstanding, because I couldn't find their pictures on the internet. These are all great people to reach out to if you're curious about radio astronomy, want to learn more about any of this stuff, or particularly these two people in the upper left, Jim Cordes and Shami Chatterjee, are great contacts if you're interested in getting involved with radio astronomy yourself here at Cornell. Thanks very much. I realize we're a little behind time, so I'll apologize for that and offer to take questions now, or I can be emailed as well.
So a round of applause, and thank you for Ben that he may or may not be able to hear. But next I'm going to welcome Marquise to talk about a slightly different angle of radio astronomy.
So yeah, we're still here on the fun part of the frequency band. Is that a good volume with the microphone? Okay, cool. So this is Crossing the Transient Universe. So this is a presentation on the work that I did this past summer. I wanted to set up this real quick. work. There we go. So yeah, I worked with Professor Anna Ho, and it was my entire summer project. So what did I do? Well, this is a supernova. It's cool. They're obviously really bright in the optical light, and we have tons of surveys that are constantly scanning the skies looking for these supernovae every night. But that's just in the optical, and so a natural question arises: what about this? What about in the other wavelengths of light? So, in particular, I worked on radio emission. So, a couple questions that we wanted to answer is: why is there a radio emission in the first place? And what can this reveal about what's going on with the star before it explodes? So that's not a very good picture, but the process is basically when the star is getting really close towards the end of its life, it starts to lose a bit of its outer mass, and it just sort of expands outwards. And then when the star goes supernova, it will hit that ejecta, and that will create a radio emission that you could then view, which I'll get to that in a second as well. So here is what I did. I did a cross-matching effort. So I took supernovae from the ZTF Bright Transient Survey. I had nearly 9,000 different supernovae, and I cross-matched them with data from the Very Large Array Sky Survey, which, for the radio astronomy nerds, BEN, it's in the S-band between 2 to 4 gigahertz, and it has these 3 distinct epochs that it ran. So it runs for about 2 years, takes a year break, and then they run again. Thankfully, the VLA is going for another couple rounds. They got their funding renewed, as did BTS. So what I did is I had nearly 36,000 cutouts of images that looked like this and this, and I had a giant HTML page, which you'll see on the next slide, and I would go through and I'd manually search for this radio emission of the supernovae. So this is a bad example. This is in fact a radio emission, but it's very clearly coming from the center of the galaxy. On the next slide, this is an example. Unfortunate. Okay, there we go. This is an example of what most of the page looked like. So a lot of it didn't have much going on there, but sometimes we did have something. So the top is an example of something that we don't really want. That is just a radio emission from the actual galaxy. But this one right here, you can see, I'll come to this side. This is, the numbers right here indicate how long after the supernovae. So for the people in the back who can't really see it, this says 25 days, this is 999 days. So 25 days after the supernova, there was no radio emission, but there was a radio emission 1,000 days afterwards. The pink square is just because there was no image for that particular epoch. This, in particular, is a tidal disruption event, if I'm remembering correctly. So what do we got? One of them is that TDE. That's actually a different one, but that is another example of something that we had found that was pretty significant. The bottom is an example of a type 2P. Both of them have been reported and been known about in the literature, so it was just really cool to verify that our process was actually working and that we were rediscovering these objects that had previously been known about. But on to the new stuff. So so I should back up a little bit. We had 9,000 different objects to look at, and after going through the entire page, we ended up with 448. So that was a great way to spend some time. And so when we had those 448, we split them up into different categories. So we had gold, silver, and bronze samples based off of how good they looked, if they were really in the center, if there was like maybe no detection at all from the previous epochs. So once we had them split up like that, we would check for alignment for the radio and the optical emission. So I developed a pipeline where I could take the radio cutout and I could send it through a program called CARTA, and that would basically just extract the exact coordinates for the radio emission. And then once I have those radio coordinates, I would see if it is in fact where the transient is. And how VLA works is how the BTS works is the transient should be in the exact center of the image. So we can be sure that that is in fact a transient and that the radio emission is from the supernova and not the galaxy. However, this is a really good example of a bad detection where you can clearly see that the detection is coming from the center of the galaxy, which is right about here. I did it again. It'll come back on in a second. Gotta be careful not to step on that. Okay, maybe it won't. Oh dear. Okay, there we go. The actual transient would be right here in the sun. There's nothing really going on right there, so we can be sure that that's not the detection. However, that is not good enough, so we wanted to get a bit more rigorous analysis of what we were doing. So we took the sources that we thought were pretty good, and we wanted to check for nearby galaxies just to make sure that it wasn't, well, if we wanted to make sure that that the center of the galaxy was further away from the transient, to make sure that we weren't looking at the galaxy, and if we weren't, then it was good. But if it's closer, then it could be a potential AGN or quasar that we were looking at the radio emission for. So then we took the ones that weren't as good, and we just looked through quasar catalogs. It's called milliquasars, and we just saw if there was a quasar associated at those exact coordinates. And if there was no quasar, then we said it was a good candidate, and if there was likely a quasar or an AGN, we just sort of got rid of it. So after we ran all of the 448 objects through all of that, I didn't mean to show this one yet. I'll come back to that. So after we ran it through, we ended up with 17 confirmed candidate transients that we thought were really good. As a quick aside, I will mention that one of the transients that we had discovered, it was a Type 1 CBL, or Type 1c broadline supernovae, and a colleague of Anna's and a colleague of mine, he was working on a paper which he was doing basically optical and radio analysis of specifically Type 1c broadline supernovae, and he did not know about the radio emission from this supernovae. So I wrote up a couple paragraphs and I sent it over to him, and that 1CBL went into a paper that was released last Tuesday. So I will now go back to this page. This is a plot by Michael Stroh from his 2021 paper. Stroh did a similar cross-matching effort like I did. However, he only worked with, I think he had 39 supernovae, and I had 8,000, so 9,000, so who's the winner? But I took the candidate transients and I overplotted them onto the plot, and you can see that they are much younger, which makes sense. The supernova catalog that I was working with only dates back about 6 years, whereas the supernovae that Stroh was working with dated back to like, I can see one on here that's going back to 1965. But even though they are much younger, they're still at a similar luminosity, which is kind of cool. And the other thing that was really cool about this is that for some of the transients that had maybe still a little bit of a detection, but just not as strong, we were able to model their light curve before, during, and after the transient. So there's a couple of them on here that you can see with the pink lines, just to show, how their light curve evolved over time. I guess it's not a real light curve because it's luminosity, but it's light. So yeah, we had those 17 confirmed candidate transients, but where do we go from here? Nowhere. We don't go anywhere. Kidding! So we ended up submitting a proposal to the Very Large Array, which we basically said, hey, we want to use your telescopes, and we want to get follow-up observations on the supernovae just to basically see what they're doing, what their radio emission is looking like, if it's still there, and what the luminosity is looking like. And thankfully, the proposal was accepted as of like 2 weeks ago. So that is the summer project that I will be working on next summer. And another idea that was presented to us from a colleague, and this is something another person in the group is doing. He is taking the radio cutout, so all of like the 36,000 or whatever we had, something like these ones, and he's stacking them all to reveal the average flux value of the detection, which would allow for deeper analysis of the radio emissions, just so we have a better and more concrete understanding of what actually is going on. And there's a picture of the VLA, which is in New Mexico. Awesome. So yeah, there are the references. There was not many, but it was the 2 papers with the previously known about objects in literature, and then Gokul's paper that went out last week. And then thank you for listening, and there's my contact information if you want to get in contact. And then questions, yeah.
In the interest of time, we might hold it till the end. Just want to give it time. In the interest of time, I think we're going to hold questions to the end, but like definitely feel free to ask them at the end if you have any. But we are going to welcome our last pair, which is going to be talking about spacecraft. So a little different, but still astronomy, but more mechy moment, I would suppose. So if Eric and Claire want to come up.
Yeah. All right. Well, welcome to the. Oh.
This one might be awkwardly loud.
Hello. Ooh.
Welcome to the best portion of the
So
student
true.
research night presentation.
Oh no. Wait. We've lost it. Did I step on a cord? Oh, it must have. I must have stepped on that one.
Let's see if it comes back. Otherwise, we might have to unplug, replug type of situation.
Causing chaos.
Do 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 do.
Oh. That's awesome.
What did you do?
Causing problems. That's a great question. Let's see.
Okay, I think the video light on the thing is blinking now. There we go.
Let's go.
Okay, check that this.
He's an EC. Now I'm definitely not going to step on wires. I've learned my lesson.
Yeah,
Go over a little bit so I'm not in front of the slides. Yippee.
yeah. So we are the cast resident Meckies.
We are.
The best major at Cornell.
Yes.
So we're just going to get started. This is exactly what Claire and I do. We
Yep.
just do this. So if you
Pictures
take-
taken directly from our research.
Yeah, exactly. This was presented at a talk like last week. Anyways, so I'm going to talk to you a little bit about sort of a time optimal version of spacecraft trajectories. This is research that I've been working on with originally Professor Mason Peck in the Space Systems Design Studio, and now with Professor Dmitry Savransky and one of his PhD students. So a little bit of background, sort of a 5-second spacecraft propulsion 101. The rocket equation, some of you know what the rocket equation is. Some of you may have learned about it in physics 1116. Basically, it says, that's a bunch of stuff from NASA, but the meaningful part of the message is that you have to carry fuel, to carry fuel, to carry fuel, to carry fuel, so on and so forth. This is why spacecraft or launch vehicles are staged, so why then you can sort of dump dead weight when you don't need it anymore. And why most spacecraft are also like 90% fuel. And then also why we go through painstaking efforts of doing I think there's one spacecraft mission going to the inner solar system that took 9 different flybys of Mercury to slow down its orbit to get in an orbit of Mercury. Really stuff like that, because we can't afford to carry that much propellant on board. And to go a little bit more, spacecraft propulsion can kind of be divided into 2 main categories. You have your chemical propulsion and your electric propulsion. And to understand the key difference, it comes down to this parameter called specific impulse, which is it's the thrust that you get out of a given type of propellant or propulsion system, normalized by how much that propellant weighs on Earth, because we are very Earth-centric beings and decided to do weight normalization instead of mass normalization. But so that basically there's this horrible thing that exists where you can either have really high thrust or really high ISP. High ISP is good. That means that you don't have to carry as much fuel. And that's where electric propulsion lays. So that's stuff like Hall thrusters and ion thrusters and stuff like that. And you're looking in the like thousands of seconds of ISP, but you're looking in the millinewtons of thrust. On the flip side of that, you have chemical propulsion, which is, if any of you have seen a video of a launch vehicle, that is chemical propulsion. You get thousands and thousands and thousands of newtons of thrust, but you have like only a couple hundred, if you're lucky, seconds of ISP. Sort of in the middle, you have nuclear thermal propulsion, which I'll get to in a little while, but that doesn't actually exist yet. And then the last thing that's sort of a 101 thing is spacecraft maneuvers. So pretty much all interplanetary travel right now is, it's called delta V optimal. So it's basically how much velocity change you need for your spacecraft, meaning also fuel optimal. And the theoretical best you can get, well, in some cases you can get better, but normally the theoretical best you can get is called the Hohmann transfer, which I'm not going to go into too big of a detail on it, aside the fact that it takes a long time. Like, for example, a trip to Mars is on the order of 170 to 200 days. So obviously this is the main reason why humans haven't explored the rest of the solar system, is because it just takes so long. So what I'm trying to answer is, in a world in which you have a high thrust, high ISP propulsion system, so note this does not exist, but it probably could exist within our lifetime. What does an interplanetary minimum time trajectory look like? And it's really not that interesting. It is a straight line, as one would expect. It satisfies the Hamilton-Jacobi-Bellman time optimality, which basically means you just hit the gas, then hit the brakes. So again, not that enlightening at face value. This was some work I did a couple years ago that said that you could basically get to Mars in like 3 days if you accelerated it a couple times the gravity of Earth, which I think 3G is what humans are said to be able to endure for a long amount of time. So just 3 times what you feel right now. But this is not at all possible. Right in this case study, we were assuming an ISP of 82,000 seconds with large thrust. It was from a theoretical paper that proposed a positron catalyzed fusion propulsion system, which is like it's like barely more than a paper. I don't think they've even done any experiments on it. But it was like, okay, whatever. So it's not practical anytime soon. So shifting gears into what I'm doing more right now, this is now looking at nuclear thermal propulsion, which is sort of that middle of the road propulsion system. So this gets you on the order of a couple thousand newtons of thrust. This is not a powerful enough propulsion system to launch you into orbit, but it is powerful enough to do larger maneuvers. And this is actually what NASA's proposing for their proposed Mars missions. All use nuclear thermal propulsion. Yeah, it is a very nice nozzle. So this isn't real yet, but NASA and DARPA are cooking on something. Last year, they announced their Draco project, which is to actually create and flight test a nuclear thermal propulsion system. This technology is not that new. There was the NERVA program back in the 60s did this, but it was, for a number of reasons, it was disbanded. But this is sort of the crux of what I'm looking at now. So why would this nuclear thermal propulsion and this continuous high thrust maneuver be good? And a lot of it comes down to the fact that nuclear thermal propulsion systems are kind of bad. In that they have, this is a table that has a comparison of traditional chemical propulsion systems and nuclear thermal systems, and the biggest thing on here is look at the difference in mass. That is an order of magnitude heavier propulsion system. And in a system where trying to minimize your mass is honestly the most important thing, that's not good. You're carrying a lot of dead weight for a propulsion system that's firing for a couple of hours on the orders of a 100-day journey. The other thing is on this plot on the left, you have really non-negligible ramp times. So your average ISP and your average thrust and your average power are very, very different from your peak power. So if you, and this is on the order of like 800 seconds are the limits of those plots. But if you're running these over like a couple of days continuously, all of a sudden your average approaches your peak value, which means that you're not dealing with these losses. And that means you really can decrease. So the idea is that we're looking at, is it better to run one of these nuclear thermal propulsion systems at a smaller scale continuously rather than at a larger scale impulsively? And I have some really janky math that proves that linear scaling of this propulsion system is not the worst assumption in the world, which I'm happy to talk to people about that later. We have had propulsion experts say it's not awful. It, of course, is not actually linear, but it's not ridiculous. But the basic idea is that this would decrease the mass of a propulsion system by a lot. So, for example, this is sort of what 2 example cislunar trajectories would look like. They are about the same time frame as, it's called the lunar free return trajectory. This is what basically all of NASA's lunar missions do. The basic idea of it is that if this is what allowed Apollo 13 to actually like come back, is because once a spacecraft leaves Earth, this trajectory will bring it back to Earth if there is no outside interference with the spacecraft, versus a lot of other trajectories would just sort of shoot off into space, which would not be great. So we're looking at comparable transit times to that. These have an order of magnitude smaller propulsion system requirement than an impulsive version would. It does have a larger delta V, so you're going to have more fuel requirement, but the proposed fuel for NTP systems right now is hydrogen, and hydrogen is not the most expensive thing in the world as compared to the mass of the propulsion system. So I just have these are just a couple figures from a paper that I'm publishing in a couple weeks. That just sort of show how these compare to, or like for a range of different thrust levels, the basic things on here is, so you can see with the delta V requirements, you can see that this is on the order of, I guess it's like 5.7 probably kilometers per second of delta V, which I won't go into the math of why delta V is important, but basically just delta V directly corresponds to how much fuel you have to carry. The propellant mass exhausted by the spacecraft is this plot on the upper right. And then I didn't really talk a lot about what the actual maneuver looks like, but there's a point at which obviously your spacecrafts have to flip around to be able to burn and fire in the direction of motion opposing the direction of motion as opposed to in the direction of motion. And this sort of shows like at what percentage of the maneuver does that happen. And then the plot on the right is in days the total travel time. And you can see that even increasing your thrust by 100 newtons over that entire couple-day transit does bring your transit time down by an entire day. Yeah, and then that's just the stupid scaling stuff. So we can move on to Claire now.
Hello, my name is Claire. I'm a part of Dmitry Savransky's lab, and I'm working on this cool thing called ExoSims, which is a mission simulator for next-gen exoplanet observatories. So a lot of people talked about some really fantastic science that they're working on, but someone has to design the things that get you all your data. So that's what this is. So why do we simulate all this stuff anyway? There are a lot of things that we still don't know about the distribution of exoplanets in our galaxy. I see you, Trey. Especially when it comes to Earth-like exoplanets. So perhaps exoplanets that have carbon-based life forms like us on them. So this makes it difficult to design technology that finds Earth-like exoplanets effectively, because we don't even know how many of them there are. We don't even know what percentage of stars have them. We have no idea. So we solve this by doing a huge Monte Carlo simulation. So what that is you pick any initial condition you can think of, basically, and run hundreds of thousands, maybe millions of simulations. and you can extract a plot from that for what your best, in this case, observatory conditions are for optimizing your yield of Earth-like exoplanets located. So Monte Carlo appears everywhere. You see it in finance, you see it in F1, you see it here, it's everywhere. So that's the baseline for why this software even exists. Why do we simulate this stuff? Part 2. So this project is kind of a subset of one of NASA's larger goals to mature optical technology to the point that we can directly observe exoplanets. So I'm going to talk a little bit more about what that technology looks like in a second. So we can do very interesting science with directly imaged exoplanets, including spectroscopy, so we can see what they're made of and see if maybe they have water on them, among other things. So how do you even simulate an observatory in Python? Python's just a whole bunch of words. How does that become a telescope? So this is where ExoSims comes in. It's an open source object-oriented Python program, and there are a couple of defining object classes that define an observing mission that are particularly important. So first, there is an object that simulates the universe. That sounds big, but you feed it a bunch of star data and a bunch of planet data and perhaps some estimations of what the density of Earth-like exoplanets is in that span of stars. And we, as a result, are able to select targets for a fake observatory at this point. So the next big thing is the observatory itself. There are a couple of different technologies that are of interest here. For direct imaging, mostly things that block out stars. So exoplanets are super dim, and if you want to look at them directly, they're already so dim that that's difficult, but they happen to be very close to these big bright objects that completely wash them out. So the best way to approach actually seeing them is to block out said big bright objects. And there are two ways that people are primarily looking at for doing that. The first is called a coronagraph. So that's an instrument that goes inside a spacecraft and it covers stars with like a spot, basically, kind of like this circle on a popsicle stick example. It's kind of a very simplified coronagraph. And as a result, you can use that to block out the super bright stars and hopefully see a couple of exoplanets. The other option is a star shade. So that is a kind of separate spacecraft that flies alongside your observatory and blocks out stars that way. They have kind of the same effect, but there are two different modes of doing that. There are also considerations for what we're using to actually image these exoplanets. So what's the signal to noise ratio? How dim are these objects that we can even see? What kind of propulsion are we using? So that's all stuff that goes under the observatory section of this code. And then the last big thing is timekeeping. So when are we scheduling observations? When are we scheduling burns of propulsion systems? What defines the end of a mission? So all of that goes into the third major object class for this program. So most of my work is going into this section. So I'm working on how to simulate observing certain targets so that we can figure out how our observatory is actually seeing them. So this is a very interdisciplinary project. We've got some astronomy, so I'm doing some astronomy right now, even as a Mechie myself. Lots of dynamics, guidance, navigation, and control, computer science, optics, general spacecraft design. We've got a ton of super fun stuff that's happening all the time in this lab. I think I have one more slide. I do. So where is ExoSims and my research in particular useful? So one big one is the Nancy Grace Roman Space Telescope, which was actually recently completed and is hopefully launching in around 2026. So some kind of versions of ExoSims are being used for target selection for a certain tech demo, which I happen to be relevant to, so that's exciting. The other big thing is the Habitable Worlds Observatory. So this is a super early stage, like pre-phase A NASA project right now. Maybe it'll fly in a few decades, and kind of the optimal goal for that observatory is to be able to directly image exoplanets and perhaps find some planets like Earth, which would be super fun. And in general, it's useful for that overarching NASA decadal goal that I talked about earlier of optimizing optical technology and maturing it over time so that we can build bigger, better telescopes and get all of you lovely astronomers out here better data. So that's all I got. Thank you.
Okay, one last round of applause for all our speakers, most of who are now sitting down. We are slightly over time, but if anyone has any questions about any of the topics, feel free to raise your hand. Otherwise, you can track down the relevant speakers. So any questions? Okay, then we will, as always, be heading over to the observatory, which everyone in this room knows is open from 8 to midnight tonight. The snow earlier today kind of made viewing abysmal, but we may be able to catch Venus, so we will see you there. And I will do one last pass at questions in the chat, but otherwise I think we're good to go. Okay, so we don't have any questions in the chat, so that is our final lecture for the semester, and keep an eye out on our website and our mailing list for information about next semester. Thank you so much.